Hi there, this video is going to be on integration and the area problem. To start out, I'd like to just go over summation notation, just as a refresher. You're probably really used to seeing this, but just for one more time. So basically, I'm just writing down what a sum is defined as. So you have your function here. You have where you start, I equals m, so it could be like I equals 7, I equals whatever. And then it goes to n, which is your endpoint. So just as a quick refresher, we're going to have the sum from I equals 2 to 7 of 4i plus 3. Alright, so if we were to go through this, it'd be 4 of 2 plus 3 plus 4 of 3 plus 3 plus, and then all the way up to 4 of 7 plus 3. Alright, and so if you were to tally all of those up, it will eventually equal 126. You see, because this would be 8 plus 3 is 11, plus 12 plus 3 is 15, and you just do that plus that plus that plus that, plus this equals, well, that. If you want to do all of them out, it's fine. It should be 11 plus 15 plus 19 plus 23, blah, 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 blah. And you'll get this answer because that's the right one. So, not going to go into real depth on that. Just as a refresher, we'll leave it at this. If you have any more questions, talk to Mr. Stewart. He's a lot better with these things than most people are because, well, he's a math teacher. He should be. So, from here, we'll just move right on in to one of the main questions and problems that we have to do. Alright, so
you may remember from last year, I'm not sure if you went over it with your class, but a thing called antiderivatives or integrals. So let's just take an example. We've got 3x squared plus 2x plus 2. Alright, this we'll call Joe. Okay, and so if you derive Joe, which you should be really good at, you just get 6x plus 2, right? Because, well, that times that is 6x, then 2. So, this is the derivative of Joe. However, what if you wanted to find what Joe was the derivative of? For example, if 6x plus 2 equals the derivative of Joe, Joe is the derivative of what? This is basically called taking the antiderivative. There are two things which tell you to do that. One is integral sign. This basically just says find what is in here, find what it is the antiderivative of. Okay, another way to see it is big F of, we'll just say x. You're pretty used to seeing their fancy f of x like that. Well, this just says take the antiderivative. So, we will erase all of this. And we'll move straight into it. I'm not sure how good you may be at this yet because, well, he did things a little differently last year. But we'll just go with an example. We'll say antiderivative of 2x dx. Alright? Now, how exactly would you get an antiderivative? There are a few rules that you'll learn as you do more and more, but to start with, let's just look at a formula, as much as you might hate it. Alright, so, y equals a to the x to the n, alright? Just a simple thing. It could be 2x to the 4th, whatever. This is just all represented by variables. And so, if you were to derive this, you would multiply that down. So derivative of y, well, not derivative of y, dy dx. It's a different thing, but anyway, dy dx equals a times n, right, because you take those down, times x to the n minus 1. Alright, that's just a simple derivative. Now, let's just make some relations, alright? If this is a derivative, then 2x equals this, a times n times x to n minus 1. Alright, because this is the antiderivative. Alright, no, this is the derivative, I'm sorry. They're both derivatives. So let's just start subbing some stuff in, alright? So, if n minus 1 is 1 over here, then n has to equal 2, right? I apologize about that. My dad interrupted and started talking about rain gutters. Basically, I'm just going to take a step back, alright? Because I got a little lost in translation and making another video. Basically, here's what we got. This is a derivative and this is derivative. Okay, so let's start doing some substitutions. Okay, so the exponent over here is 1. Okay, and so n minus 1, just to make this blatantly obvious, alright, because those two have to equal each other. So n minus 1 equals 1, n equals 2. Alright, we all agree on this. Of course we do. So 2x equals, and since n equals 2, we can substitute it in there and there, equals a times 2 times x to the n minus 1, or just 1. Alright? Now, we can find a, because in this case, the only thing times 2 that will equal 2 is 1. So a equals 1. Okay? So, a equals 1, n equals 2. We then plug those into the original function that we derived. Okay? So, y equals a times x, which is just 1 times x, to the n, which is 2. Alright, and this is the antiderivative of this. Alright, now you won't have to go through this whole process every time, but this way just kind of spells it out algebraically. You're going to, as you go on, find out more. Oh, sorry, did forget one thing, plus c. Okay, now as you go on, you're going to find out more rules and tricks that you can use to get antiderivatives. You know, it'll get to the point where you see that and, you know, you're overjoyed because it's so unbelievably easy. So you've got a long haul in front of you. But you can do some pretty cool stuff with it once you get the hang of it. Now, you probably are wondering why I added the plus c. Well, let's just use an example. If you derive 3x squared plus 5, the derivative of that is just going to be 6x, right? If you derive 3x squared plus 50, it's still just going to be 6x. If you do 3x squared plus 5,000, it's still going to be 6x. Doing the plus c basically means that your antiderivative covers all of these constants. It won't give you a specific one, but it will cover them all. It's like saying my mother's side or my father's side. You're not listing off every specific relative, but you are kind of grouping them all together. That's the only thing that plus c means. And some people are really militant about it, so just make it a habit. Alright. Let's look at a couple rules that'll make things easier for you later on. We'll do the integral of kx dx, where k is just a coefficient, so it's like 6x or 1/2 x, or even a function. That you can pull out, which is going to come in handy much later on. Well, not much later on, but it's going to come in a lot of handy. I don't know. It's going to be very helpful for you later on. And you're going to want to make sure that you always remember that one, because it comes into play a lot. Another good one to remember, oh wow, fat little line. Another good one to remember is when you have two different functions within your integral, plus or minus g of x. Basically, what you can do with this is you can make it two separate integrals, and that'll also be really helpful later on, because as you start getting more and more complex integrals, you're going to want to find ways to simplify them, and these are both ones that you will want to remember. Now let's take a look at the area problem. I don't think it's actually a huge problem, but it actually ends up being one. So let's just, we have our graph, right? And we want to find out, okay, this is x squared. We want to find out what the area is from 0 to 2 underneath this curve, okay? Now, if I gave you a rectangle and said, what's the area? You would basically say, well, it's the base times the height, because, well, that's what we've learned since 3rd grade. Essentially, what people have looked at doing is, to start with, they say, well, you could potentially draw a lot of little rectangles on this. So let's just start with some not really little ones, but they're there. Okay, so that's 1, that's 2, and there's actually two ways to draw these rectangles. But for our purposes, well, not even for our purposes, I'll just say this. This is called an upper sum because you're including, that much more than is actually under the curve. All right? The other way that you could draw that is called a lower sum, where you take less. All right? Now, I'm going to draw 2 graphs for you, and this is all part of it. Now, if I were to just draw 3 rectangles, all right, and these aren't perfect, but just pretend that they are. Okay, so these ones are all more than the line, and these ones are all less. And so the best way that you could overcome that would be to draw even more rectangles. Just because I don't want to draw 2, I'll just draw this one really, really big. You notice that as the rectangles get smaller, there's less and less wasted space. So theoretically, if you had an infinite number of little itty-bitty rectangles, you would have the correct amount of space. This is what is called the limit definition of the area. Essentially, you have the limit. Wow, that's really, really gross looking. You have the limit as the number of rectangles you have approaches infinity of the sum of those rectangles. Basically, this is just shown by the sum as it goes to n, which is basically infinity, starting at 1, I guess, of your function times the change in x. So you're probably wondering what this is. Your function, that's pretty self-explanatory. There we go. F of c of I basically is your height. Okay? So, on a rectangle, you have your height and you have your width. Okay? Now, if you were to find the height of a rectangle on a graph, yeah, those are x and y axes. If you wanted to find the height at that point, you just plug in this point right there. That's basically all it's saying. Your height is going to be whatever f is at that point. Okay? Now, the delta x, a change in x, basically is just how much is it changing, or your width. So if you have one there and one there, the change to there is going to be different than the change there. But with these kinds of sums, the changes are going to be the same. For example, they're both that much, which let's just say they're equals, okay? Okay, now earlier when I mentioned the plus c stuff, and I have blah 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 plus c, that's basically called an indefinite integral. Because this could be literally anything. So it really isn't sure about what it wants to be when it grows up. However, there are also definite integrals. The more astute ones of you probably would have figured that out by now. And the only way you know the difference between these two is if it has those. Okay? Now, let's just take a quick antiderivative rule. Alright? So, we'll take the indefinite integral, no a and b, of x squared dx. Alright? So, I'll just use my immense brain power and Stewart-given abilities and just do this in my head. Alright? So, you guys can do this out for yourself. In fact, it might be easier just looking at it. 1/3 x to the third, alright? Multiply that down equals 1. 3 minus 1 is 2. Okay, we're good on that. Okay? Now, that is indefinite, so it needs a plus c. However, if I said definite, then you'd have to take this, x squared dx, x to the third, and then you apply what is called the fundamental theorem of calculus. Alright, now, this is a really, really handy little dealy whopper, and it goes as follows. Okay, the antiderivative with b plugged in, which is this, minus the antiderivative with a plugged in, which is that, equals your area. Okay, so instead of having to use that limit process for every single one, you can just use this, which is a lifesaver. Okay, so let's just do it for this one. Alright, so we have our antiderivative, or big F. Okay, so we just plug in b and then a in for x. So 1/3 times b, or 3, to the third, minus, okay, 1/3 times a to the third. Alright, so we'll just add this up. 3 to the third is 27, divided by 3 is 9, minus 0 equals 9. Okay? So, on this curve, on x squared from, I'll just draw it out, from 0 to 3, that all equals 9. Alright? Which is pretty dandy, or nifty, or spiffy. It depends on which one you like the most. One last thing. Sometimes, well, let's just draw another graph. We'll say that's 3 and that's 5. Okay? Now, sometimes you will have a graph that goes below the x-axis. Okay? And for the ways that we've been doing so far, the area was only taken from the x-axis up. Okay? Now, this isn't a huge deal. You just have to do a couple special rules. And actually, they're really not that simple. Basically, what you want to do is find the area from this point to this point. So, you take the integral, and this isn't the correct formula for it, but let's just do 3x squared plus 7, okay, from 0 to 3, okay, and then add that to this area. Now, this area may or may not be negative. If it is, I mean, who has negative area? That doesn't even make sense. So, if it is negative, this probably isn't very kosher, but I always just make it positive, because realistically, who cares? And second of all, if it is positive, you may or may not have done something wrong. So, you'll figure it out. Okay, and then you would add it from your next section, from 3 to 5 of this, and then you would once again add it, and it depends on how far you're going. Let's just say that's 7. Then you would add that to from 5 to 7 of blah. And so it may look a little scary at first, but I'm sure you guys will be fine with it, and you're smart enough to make it to calculus. You're smart enough for anything.